Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. This week on the podcast, I'm excited to present a series of interviews exploring the emerging field of differential privacy. Over the course of the week, we'll dig into some of the very exciting research and application work happening right now in the field. In this, our first episode of the series, I'm joined by Aaron Roth, Associate Professor of Computer Science and Information Science at the University of Pennsylvania. Aaron is, first and foremost, a theoretician, and our conversation starts with him helping us understand the context and theory behind differential privacy, a research area he was fortunate to begin pursuing at its very inception. We explore the application of differential privacy to machine learning systems, including the costs and challenges of doing so. Aaron discusses as well quite a few examples of differential privacy in action, including work being done at Google, Apple, and the US Census Bureau, along with some of the major research directions currently being pursued in the field. Thanks to Georgian Partners for their continued support of the podcast and for sponsoring this series. Georgian Partners is a venture capital firm that invests in growth stage companies in the US and Canada. Post-investment, Georgian works closely with portfolio companies to accelerate adoption of key technologies, including machine learning and differential privacy. To help their portfolio companies provide privacy guarantees to their customers, Georgian recently launched its first software product, Epsilon, which is a differentially private machine learning solution. You'll learn more about Epsilon in my interview with Georgian's Chang Liu later this week, but if you find this field interesting, I'd encourage you to visit the Differential Privacy Resource Center they've set up at gptrs.vc/TWiMLAI. And now, on to the show. All right, everyone, I am on the line with Aaron Roth. Aaron is Associate Professor of Computer Science and Information Science at the University of Pennsylvania. Aaron, welcome to This Week in Machine Learning and AI.
Thanks. I'm glad to be here.
Why don't we get started by having you tell us a little bit about your background and how you got involved in the machine learning field?
Sure. So I'm a computer scientist, and I guess I would describe my background as really coming from theoretical computer science. So as someone who, sits down and tries to understand things by thinking mathematically and proving theorems. And the way I came to machine learning in general is, well, from a background in learning theory, and in particular, the flavor of problems that I've studied, both sort of historically and now, have to do with the way that machine learning as a technology interacts with things that you might more normally think of as societal concerns. So things like privacy, things like fairness, and things that maybe more typically an economist would think about, like how do machine learning algorithms work in strategic situations.
You're also very involved in the work happening around the application of differential privacy to machine learning. How did you get started down that route?
Well, so I started my PhD in 2006, which is the same year that the first paper on differential privacy was published by Cynthia Dwork and Kobe Nassim and Adam Smith and Frank McSherry. And so this was a very new topic at the time that I was just starting to think about research. And, it struck me as timely and important. And at the same time, when I was just starting to think about it, not much was known. So it was sort of at the sweet spot for PhD theses where you can study an important problem and have a lot of impact without having to do anything too clever.
Well, maybe a good place to start in our exploration of differential privacy and machine learning would be to have you define differential privacy and tell us a little bit about the context in which it was created.
Sure. So privacy has a relatively long history in computer science, but until people started thinking about differential privacy, what people meant when they said privacy was some kind of syntactic constraint on what the output of a computation could look like. And it turns out these kinds of syntactic privacy guarantees don't have a strong meaning in terms of privacy, and there was sort of a cat and mouse game in which people would attempt to share data sets with some kind of privacy protections, and then some clever person would come around and figure out how to get around those privacy protections, and this would iterate.
Can you give us an example of those types of syntactic constraints and, a little bit of how that cat and mouse game evolved?
Sure. Yeah. So maybe the, simplest thing that you might imagine is you might think to yourself, well, if I just remove any identifying attributes from a data set. So for example, if I've got a data set of medical records, if I just remove things like name and zip code and maybe a few others, that'll anonymize the data and it'll be safe to release the data set in the clear. And unfortunately, that turns out not to be the case. So there's a bunch of examples of this sort, but maybe the first one was a demonstration by LaTanya Sweeney. At the time, she was a PhD student at MIT. Now she's a professor at Harvard. And the state of Massachusetts had released a supposedly anonymized data set of patient medical records. So it didn't have people's names attached. But what LaTanya figured out was that there was another data set that was publicly available. That was the voter registration records in Cambridge, Massachusetts. And, when you've got two data sets and you know something about an individual, for example, LaTanya knew that the governor of Massachusetts at the time, William Weld, lived in Cambridge. I knew a few other things about him. You can basically cross-reference these two data sets and reattach names. So that's sort of the simplest example for why attempting to remove identifying attributes doesn't work. It seems like a good idea in isolation, but in the real world, there's all of this information out there that you can attempt to cross-reference with existing data sets.
I think another example along those lines was when Netflix released their anonymized recommendation data set for, I think it was the Netflix Prize. Someone or set of people cross-referenced that to IMDb and found that they were able to de-anonymize a pretty significant portion of those records.
Yeah, that was another high-profile example using a more sophisticated technique that was done by Arvind Narayanan, who is now a professor at Princeton, and Vitaly Shmatakov, who's at Cornell Tech. And that was another example where, names were removed. All that was made available was sort of a big data set where for each person now identified by a, supposedly anonymous numeric identifier, all you saw about them were which movies they watched, what they rated them, and approximately when they watched them. And as you say, by cross-referencing this data set with IMDb, they were able to reattach names.
So differential privacy came about kind of in the wake of the broader realization of the failure of anonymization, it sounds like.
Exactly. So I think the key insight that the creators of differential privacy had was that, if you want to speak rigorously about what someone can infer about an individual, given what they observe about an algorithm, you shouldn't be trying to put syntactic constraints on the output of that algorithm, but rather you should be putting information theoretic constraints on the algorithmic process itself, on the computation. And so that's exactly what differential privacy does. What differential privacy means informally, it's a constraint on an algorithm, and it says small changes in the input to an algorithm, for example, adding or removing the record of a single individual, should have only small changes on the distribution of outputs that the algorithm produces. So if I remove your record entirely from a data set, that shouldn't cause any observable event, anything that the algorithm might do when computing on the data set, to become too much more or less likely. And this kind of probabilistic information theoretic constraint turns out to have a really strong semantics about what an adversary, an attacker can infer about your data.
One of the subtleties in the way you describe that is that and maybe it's not so subtle, but differential privacy isn't an algorithm itself. It's a constraint on an algorithm. Is that, am I hearing that correctly?
That's right. Yeah. So differential privacy is a property that an algorithm, might or might not have. Any particular algorithm might be differentially private or might not be. And a lot of the definition, of the constraint, it's relatively simple, but a lot of the science that goes into studying differential privacy asks the question, if I've tied my hands in this way, in what kinds of algorithms I can use, what tasks can I still perform? And as you say, differential privacy is a family of, it's a constraint. It's not an algorithm. So to show that you can do something subject to differential privacy, it's sufficient to exhibit a differentially private algorithm that does that thing. But to prove lower bounds, to show that for some problem you cannot solve it subject to differential privacy, that's another matter entirely. You have to write down a mathematical proof that no algorithm could solve it subject to the constraint.
So how does that relatively simple sounding constraint lead to the benefits of privacy?
I guess most basically, it provides a guarantee of plausible deniability. So maybe to make things less abstract, let me give you an example of a very simple, intuitive, differentially private algorithm. So suppose that I want to conduct a poll, and I want to find out amongst all of the citizens in Philadelphia, how many of them voted for Donald Trump in the last election.
Okay.
The most straightforward way to do this is I would call up some random sample of individuals on the phone, and I'd ask them, did you vote for Donald Trump in the 2016 election? And I'd write down their answer on a piece of paper. And then when I was all done, when I'd called sufficiently many people, I'd tally up their answers. I'd find that 15% of people voted for Donald Trump. I'd do some statistics to attach error bars to that, and then I'd publish the statistic.
Okay.
Now, note that the thing that I wanted to find out was just this property of the distribution, what fraction of people voted for Donald Trump. But incidentally along the way, I accumulated this large body of potentially sensitive information, what individual people voted for, who individual people voted for.
Right.
Okay, so think about the following alternative polling procedure, which turns out to be differentially private and will allow us to figure out the distributional statistic we care about, what fraction of people voted for Donald Trump, without having to collect sensitive information about individuals. Okay, so I'm going to, again, call up some large collection of people. But now, instead of instructing them to tell me whether they voted for Donald Trump, I'll tell them the following thing. I'll say, flip a coin. If it comes up heads, tell me truthfully whether you voted for Donald Trump or not. If it comes up tails, though, tell me a random answer, by which I mean flip the coin again and tell me Trump if it came up heads and tell me not Trump if it came up tails. So, and importantly, you're not going to tell me how the coin came out.
Right.
Okay, so I hear Trump or not Trump, but I don't know how your coins were realized. So I don't know whether you're telling me the truth or whether you're lying simply because of how the coins were flipped.
Mm-hmm.
Okay. So on the one hand, you now have a significant amount of plausible deniability. Okay, if all of a sudden the country collapses into a police state and my polling records are subpoenaed and you're called in front of the Truth Commission and it's suggested that you voted in one way or the other, you can reasonably say, no, I didn't. Right? The answer that you're reading was simply the result of a coin flip because I was following this randomized protocol.
Right.
Okay, so you have plausible deniability. That's the guarantee of privacy. On the other hand, even though I cannot form strong beliefs about what any individual's data looks like, in aggregate, I can. I can figure out to a high degree of accuracy what fraction of people voted for Donald Trump. And that's because I understand the process by which noise was injected into these measurements. Okay, so in aggregate, the noise behaves in a very structured, easy to understand way, and I can subtract that noise out of the average, even though I cannot figure out for any individual who they voted for.
That strikes me as somewhat counterintuitive in that, thinking about the coin flip, almost half of your data could be corrupted, or a quarter, maybe.
A quarter, exactly. So if you think about it, right, it's a simple calculation. If I know that for every individual, 3/4 of the time they're telling me the truth, and a quarter of the time they're telling me the opposite of the truth, then say 15% of people in Philadelphia truly voted for Donald Trump, I can write out on a piece of paper what percentage of people in expectation should report to me under this protocol voted for Donald Trump.
Right.
And because I've got a bunch of independent samples, the actual number of people who end up telling me this will be highly concentrated around its expectation.
Right.
And therefore, what I need to do as the pollster is work backwards. What I know is the number of people who actually told me they voted for Donald Trump. But because I can compute this one-to-one mapping between the number of people who really did and the number of people I expect to tell me this, I can invert the mapping and figure out what the underlying population statistic was to a high degree of accuracy.
Okay. It sounds like, the method you're describing could be used both prior to data collection by instructing your respondents to follow this algorithm, or if you're an organization collecting data, you could collect the actual responses and then apply this algorithm before publishing the data.
That's right. So the interaction that I described to you was what's called the local model of differential privacy. And, in this scenario, people's privacy was protected even from the pollster.
Okay.
Right? Because he never wrote down the data. And of course, if that's what you want, then you have to apply these protections when the data is being gathered.
Right.
But as you say, if I'm an organization that's already got the data, I can apply privacy protections to the output of my computations, to anything I release. So then obviously privacy isn't protected from me, the organization that has the data. I've already got the data in the clear, but assuming there are no data breaches and no subpoenas, differential privacy can guarantee something about what any outside observer can learn about individuals in the data set by observing the outcomes of computations.
And you're careful to say guarantees something. What exactly does differential privacy guarantee, and what does it not guarantee?
Yeah, so one thing that has been elided in this discussion is that there's a quantitative parameter that comes with differential privacy. It's called epsilon. But what differential privacy guarantees formally is that no event becomes much more likely if your data is in the data set compared to if it's not. But what does much more likely mean? That means more likely by some multiplicative factor that depends on this parameter epsilon. So suppose epsilon is small. This is a pretty good guarantee because it says whatever it is that you're worried about from the perspective of privacy, whatever harm you're worried that the use of your data will cause to befall you, that harm is, even though I don't know what you're worried about, I can promise you that the risk, the increased risk of that harm befalling you can be bounded as a function of this parameter epsilon. But of course, if epsilon is very big, then that's not a very strong guarantee. So it doesn't really mean anything if someone tells you that their algorithm is differentially private, unless they also tell you what this privacy parameter is. As the privacy parameter goes to infinity, differential privacy is no constraint at all. As it goes to zero, it becomes a very strong constraint.
Going back to this fundamental constraint, it's that, within the bounds of epsilon, adding or removing an individual piece of data won't change the statistics of your overall distribution. Is that correct?
That's right. It won't change the behavior of your algorithm. Okay, so adding or removing a single data point won't cause your algorithm to do something that is very different from the point of view of an observer.
And so how do we get from there to, again, the notion of privacy? And I guess you were setting that up in talking about the plausible deniability example.
Yeah, there's a couple of interpretations of differential privacy, and I can walk through a few of them. So one is this plausible deniability guarantee, right? So if someone accuses you of having some particular data record, and the piece of evidence they have at their disposal is the output of a differentially private computation, you have plausible deniability in the sense that you can say that the piece of evidence they have in hand is essentially as likely to have been observed, again, up to this factor relating to the privacy parameter, if your data had been different. Okay. Another way of saying this is, suppose they've got some prior belief about what your data point looks like, and then they observe the output of a computation, and so they update their belief to some posterior belief using Bayes' rule, for example. Then what differential privacy promises is that they would have performed nearly the same update and therefore had nearly the same beliefs had your data been different, if we hold the rest of the data set fixed. Another interpretation is this model of harm, right? And you can view this as a sort of utilitarian definition of privacy. Like how hard is it for me to convince you to contribute your data to my data set if I'm going to use it for some statistical analysis? Well, why wouldn't you want to contribute your data? There's any number of reasons, and I might not know what they are, but presumably you're worried that as the result of the use of your data, something bad is going to happen to you. Maybe your health insurance premiums are going to rise, or maybe you're going to start getting drunk phone calls during dinner. And what differential privacy can promise is no matter what event that you're worried about, and I really mean no matter what event, so we can talk about the probability that your health insurance premiums rise or the probability that you get spam phone calls, this event will have almost the same probability up to, again, this privacy parameter in the following two hypothetical worlds. In the one world, you don't contribute your data to the computation, and in the other world you do, and everything else is held constant between these two worlds. That's the difference in differential privacy, right? So if I look at the two different worlds that are identical except for this one fact, whether you contributed your data to my analysis or whether you did not, then the events that you're worried about, whatever they are, become almost no more likely when you contribute your data.
And does that interpretation, it sounds like that assumes some anonymization?
It doesn't assume anything. All that follows sort of directly from the definition of differential privacy. That, if you like, that is the definition of differential privacy.
Mm-hmm. I guess I think I'm thinking of this in some perverse way, but if I include my data and my data includes my phone number, how does differential privacy address that?
Oh, well, your data can include anything you like, including your phone number, but a differentially private algorithm certainly can't look at your data record and publish your phone number.
Right. And so is the idea that we're applying the coin flip, for example, to the publishing, maybe it would randomly spit out phone numbers or something like that?
Yeah, I mean,
I think I'm getting stuck in a rat hole here, but
so maybe one thing that's useful to keep in mind, you can try to write down a differentially private algorithm for anything you like, but it's only for certain kinds of problems for which differentially private algorithms are going to be able to do anything useful. And those are statistical problems where the thing that you want to estimate is some property of the underlying distribution. Right? So it's very good for sort of machine learning if I want to learn a classifier that on average makes correct predictions. But if I want to learn what your phone number is, it's all well and good that I want to learn that, but by design, there is no differentially private algorithm that will give me a non-trivial advantage over essentially random guessing. Differential privacy isn't compatible with answering the kinds of questions that have to do with just a single individual, and that's by design.
So that's a great segue to the applications of differential privacy in machine learning. Can you maybe start by talking about the specific machine learning, problems or examples that differential privacy is trying to address in that application, and maybe talk through some of the specifics of how that's done?
Sure. So there's a couple of things that you might want to do subject to differential privacy when you're doing machine learning. So one is just that you might want to solve a single machine learning problem subject to differential privacy. So maybe you've got some, for example, supervised classification task. You've got some labeled data you'd like to learn, a support vector machine or a neural network of some sort that will minimize some loss function, maybe my classification error, when I apply it to new data. Okay, so that's so just the standard machine learning problem, and differential privacy is extremely amenable to this kind of problem, essentially because, there's several reasons, but maybe the most fundamental reason is that this is inherently a statistical problem in the sense that the thing that I already, for reasons of overfitting, wanted to avoid when I'm solving a machine learning problem, depending too heavily on any single data point.
Right.
Okay, so machine learning and privacy, they're sort of aligned in the sense that they're both trying to learn facts about the distribution without overfitting to the particular data set I have on hand. Right? Overfitting is closely related to privacy violations, and we can talk more about that. The connection turns out to go both ways. Another thing that you might want to do is more ambitious. You might want to construct a synthetic data set, by which I mean, like, rather than solving a single machine learning problem, maybe you want to construct a data set that looks like the real data set with respect to some large number of statistics or machine learning algorithms, but is nevertheless differentially private. So I can construct this synthetic data set with a private algorithm and then release it to the world, and then other people can go and try to apply their machine learning algorithms to this synthetic data set, the hope being that insights that they derive, classifiers they train on the synthetic data set would also work well on the real data set. Mm-hmm. And then finally, and this relates back to the connections between differential privacy and overfitting, it might be that you don't care about privacy at all in your application, but you want to, for example, repeatedly test hypotheses or fit different kinds of machine learning models while reusing the same holdout set over and over again, maybe because it's too expensive to get more data. Now, normally this would be a really bad idea. Sort of the standard test train methodology in machine learning entirely falls apart basically if you reuse the holdout set as part of an iterative procedure by which you're choosing your model. But as it turns out, when you perform your entire pipeline of statistical analyses subject to the guarantees of differential privacy, you can't overfit. So if you can be accurate in sample, you can be guaranteed that you learn an accurate model out of sample, even if you've repeatedly reused the data.
And when you say perform your entire pipeline subject to the guarantees of differential privacy, does that mean you are enforcing those constraints at every individual step, or relative to the inputs and outputs of the entire pipeline?
It means that everything, you shouldn't have touched the data in any way using a non-differentially private algorithm. So differential privacy has a very nice property that it composes. If I have two algorithms, the first one is epsilon1 differentially private and the second one is epsilon2 differentially private, then if I run the first one and based on the outcome decide what I want to do at the second step, and then I run the second algorithm, this whole computation is in aggregate epsilon1 plus epsilon2 differentially private. Okay. So, if at every decision point I'm making my decision about what to do next as a function only of differentially private access to the data, then you've got these strong safety guarantees about overfitting.
So maybe to make it a little bit more concrete, I've heard a few examples of scenarios that pop up in the machine learning world, and I'm vaguely recalling them. Maybe you can provide a bit more detail, but one of them was an example of it was like reverse engineering an object detector to determine whether an individual, or a face detector to determine whether an individual face was in the training data set.
Okay, so you're talking about maybe an attack on a classifier that wasn't trained in a differentially private way, and the kind of thing that you might, the kind of reason why you might want to have privacy guarantees when you're training a learning algorithm, that they don't come for free. Exactly. Yeah, so I think there's a couple of these kinds of attacks now, and I don't know the details of the specific one you're referring to, but you might have, a priori, before you started worrying about privacy, think that, okay, maybe if I'm, releasing individual data records, like in the Netflix example, I have to worry about privacy violations. But if I'm just training a classifier, how could releasing only the model parameters, the weights in the neural network, possibly violate anyone's privacy?
Exactly.
Yeah, and that intuition is wrong, and you're describing the kind of attacks that show that it's wrong. But the basic, I think, premise underlying these attacks is that when you train a model without differential privacy, it'll tend to overfit a little bit, even if this doesn't really affect the model performance. But what you find is that, when you try to classify a face, for example, that was in the training data set, the model will tend to have higher confidence in its classification than when you try to classify an example that was not in the training data set. Okay, and it's sort of natural that you would expect that because the model got to update itself on the examples in the training set.
Right.
And by taking advantage of that, you can therefore figure out whether a particular person's picture was in the training data set or not by examining what is the confidence in the model's prediction.
Okay. Are there other examples that come to mind of, where the notion of distributing models or more generally, I guess, statistical aggregates can fail to be privacy preserving?
So maybe the most obvious example is a sort of naive training of a support vector machine. So the simplest way to, the most concise way for me to describe to you the model of a trained support vector machine is by communicating to you the support vectors. But the support vectors are just examples from the training data set. So the most straightforward way to distribute a trained support vector machine is to transmit to you some number of examples from the training data set in the clear.
Mm-hmm.
So that's sort of obvious once you realize it, but is one of the things that you might not have thought of initially if you're coming from this position, that things that represent just aggregate statistics like trained models shouldn't be disclosive.
Okay. What I'm hearing is, I guess granted in some classes of problem, maybe privacy isn't, the greatest concern. But if differential privacy were free and easy to apply everywhere, I might do that. What are some of the, the issues or costs of applying differential privacy that come up when trying to apply it in a machine learning context?
Yeah, so it definitely doesn't come for free. And I think there's costs of two sorts. So the first is sort of maybe it's difficult to just acquire the expertise to implement all of these things at the moment. A lot of the knowledge about differential privacy at the moment is contained in hard to read, academic papers. There's not that many people who are trained to read these things. So if you're just some random company, it can be hard to even get started. But maybe the more fundamental thing is that although differential privacy is compatible with machine learning, by which I mean, in principle, any statistical problem that is susceptible to machine learning absent differential privacy can also be solved with machine learning with differential privacy guarantees. The cost is that if you want strong differential privacy guarantees, you'll need more data. And if you want the privacy parameter to be small, this thing that governs the strength of the privacy guarantee, you might need a lot more data to achieve the same accuracy guarantees. So as a result, it can be a tough sell to apply privacy technologies in a setting in which developers and researchers already have direct access to the data set, because the data set's not getting any bigger. So if yesterday you could do your statistical analyses on your data set of 10,000 records, and today I say, now you've got to do it subject to differential privacy, the accuracy of your analyses is going to degrade. The place in which I've seen it successfully deployed, overcoming sort of this kind of objection in industry, has been in settings where because of privacy concerns, developers previously didn't have access to the data at all, and they're now, once strong privacy guarantees are built in, are able to start collecting it. So it's a much easier sell if the privacy guarantees are going to give you access to new data sets that previously you couldn't touch because of privacy concerns than it is to sort of add on ex post when previously you were able to ignore privacy. Right? The cost of privacy will tend to come in the form of less accuracy in terms of your classification error, for example.
Okay. Some of the known uses of differential privacy are at places like Google, Apple, Microsoft, and the US Census Bureau. Are you familiar with those examples and what they're doing? And can you talk about the ones that you are?
Sure. So Google and Apple are both using differential privacy in the local model. This model of the polling agency trying to figure out how many people voted for Donald Trump in the example that I gave. Okay, so both of them are collecting statistics. Google in your Chrome web browser and Apple on your iPhone, in which the privacy protections are added on device. And what they're trying to do are collect simple statistics, population-wide averages. So if you look at the Apple paper, for example, they're collecting statistics on, like what are the most frequently used emojis in different countries, or for different websites, what fraction of people like it when videos automatically play as opposed to requiring some human intervention. So they're trying to collect population-wide statistics that allow them to improve user experience, or improve things like predictive typing, things like that.
Mm-hmm.
The US Census is doing something more ambitious, and the US Census collects all the data in the clear, right? So they're not trying to protect the privacy of your data from the census. They're collecting it. Instead, they're using differential privacy in this centralized model. But they release huge amounts of statistical information. So, you can go on existing census websites and, figure out the answers to questions like, how many people live in this collection of zip codes and work in this other collection of zip codes. Okay. And they're going to continue releasing these large amounts of statistical information about the U.S. population, but for the 2020 census, they're going to release it subject to differential privacy protections.
Interesting. And so they're releasing not individual data records, but more these statistical aggregates subject to differential privacy.
That's right. So in all of these applications, what's being released are statistics rather than actual synthetic data sets.
Right.
As far as I know. I don't know the details of what the census plans to do, and I'm not sure that's even been pinned down. Mm-hmm. In an academic setting, I have a former student, Stephen Wu, who's now a postdoc at Microsoft Research. But when he was here, he worked with colleagues in the medical school, a professor named Casey Green, to construct differentially private synthetic medical data sets. So medicine is a field that's got a big problem in that there's a lot of data, and it's starting to be susceptible to yielding all sorts of wonderful insights if we apply the latest machine learning technologies to it. But medicine is a domain where there are serious privacy concerns and legal regulations, and so it's very difficult to share data sets. Ideally, you'd like to share your data sets with other researchers, allow them to reproduce the kinds of experiments you did on the data, combine data sets. And so what Stephen and his colleagues did was they gave sort of a proof of concept that you could use techniques for privately training neural networks and combine those with techniques for generating synthetic data for training GANs that would let you create synthetic data sets that you could release to the public, but that would look like the original data set with respect to a very large class of machine learning algorithms. So you could train the algorithms on the synthetic data and then find that when you evaluated them on the real data, they did pretty well.
Okay. Interesting.
This is the kind of thing. This is sort of the more ambitious kind of technology that I think, as far as I know, has so far been the domain of only academic research. But maybe in the coming years, we'll find industrial and government applications.
Can you maybe share a brief word on the current research areas in and around differential privacy and machine learning?
So, there are many and diverse, and there are people focused on more practical problems and more theoretical problems. I myself, just through my natural proclivities, tend to focus on sort of the more theoretical problems. But I think that it remains, even though it's an old problem, it remains an important and unsolved problem to figure out sort of practical ways to generate useful synthetic data for large collections of tasks. We've known for a while, since my PhD thesis, that these kinds of problems are possible in principle. There are inefficient information theoretic, kinds of algorithms that accomplish them, but we don't yet have practical algorithms. I think that remains very important. Another important direction is that a lot of the academic literature to date has really focused on this central model of data privacy, where there's a trusted database curator who gathers all the data in the clear, in part because you can do more stuff in that model, so it's attractive to study it. But as we've seen differential privacy move from theory to practice, to date, its two largest scale deployments at Google and Apple are both in the local model. And there's a lot of things, I think, that we understand in the central model of differential privacy that we still don't understand in the local model. And that's too bad, because the local model's turning out to be very important. So I think understanding basic tasks in the local model continues to be very important. And I mentioned briefly this sort of research agenda showing that you can use differential privacy to avoid false discovery and overfitting, even when you don't care about privacy. I think this is one of the most general promising directions to, attack the statistical crisis in science. But so far, we're just in early days. We understand the basic sort of proof of concept kinds of results for why techniques from differential privacy might be useful, but we're a pretty far way off from having practical tools that, working data scientists can use to prevent overfitting with practically sized data sets.
Okay, great. We will share a link to your website so folks can take a look at some of your recent work and publications in this area. Before we close up, is there anything else that you'd like to share with the audience?
No, thanks for listening. And, I'm always happy to hear about interesting new applications of differential privacy. So feel free to send me emails. When I was just getting started and writing my PhD thesis, all of this was a theoretical abstraction, and it's been great fun, hearing about and consulting with companies that are actually putting this into practice. So it's been a fun ride, and I like to hear what's going on out there.
Fantastic. Well, thanks so much, Aaron.
Thank you.
All right, everyone, that's our show for today. For more information on Aaron or any of the topics covered in this episode, head on over to twimlai.com/talk/132. Thanks again to our friends at Georgian for sponsoring this series, and be sure to visit their Differential Privacy Resource Center at gptrs.vc/TWiML for more information on the field and what they're up to. And of course, thank you so much for listening, and catch you next time.